Now, when we talk about introductions, some people genuinely need none because their work really speaks louder than that. But for the sake of formality, let me try to do this. As everyone probably knows, among other things, Professor Friston is known for inventing statistical parametric mapping, voxel-based morphometry, and dynamical causal modeling. But perhaps his best known contribution to theoretical neurobiology is the free energy principle. He is also the most cited neuroscientist in the world and has received numerous accolades, including several honorary doctorates from several universities. And it is truly a privilege to have him with us today. So without further ado, Professor Friston, you have the floor, and thank you very much for joining us today.
Well, thank you very much for having me. That was a wonderful introduction, given that you weren't expecting to have to do it. I often say you should also make it clear that I don't have a PhD yet. So if anybody's got any open PhD positions, I'll be very grateful. But again, thank you for having me, and thank you for that lovely introduction. Let me try and share my screen. I may need to be. Good. So I'm going to talk indeed about my favorite subject, which is the free energy principle and active inference in the brain. I usually start this talk by apologizing. I am told that it takes at least 3 times to see this talk before the simplicity of the message gets through. I should also apologize that towards the end, we're going to do a little bit of maths, largely to look at some of the beautiful symmetries that emerge from a formal or mathematical approach to how we make sense of our world and indeed make decisions and navigate around that world. So I'm going to talk, and I'm assuming that you'd like me to talk for about 50 minutes or an hour?
Yes, about 50 minutes. So we also have some time for questions from the audience.
Right, so we have to fit the questions into the hour.
Yes, if you prefer to have questions throughout the talk, we can also do that, but we usually do it at the end.
Right. No, that's important because I usually find the questions and answers are the most interesting part of the talk. So I'm going to go very, very quickly. So if you can tell me when we've got about 10 minutes left towards the end, I'll just race through the last few slides. So I apologize. This is going to be quite breathless. It's the purpose of this talk is really to go right back to basics and try to understand the fundaments of our the way in which we make sense of our lived world. First of all, looking at that issue through the eyes of a physicist and just asking questions about the nature of biotic self-organization and life, with a special focus on Markov blankets and what emerges from Markov blankets, which we will see is a kind of Bayesian mechanics or a way of understanding self-organization in terms of inference. I'm then going to tell exactly the same story, but using the language of a cognitive neuroscientist, specifically looking at predicted coding and how that is implemented in neural networks. And then if we have time, I'm going to finish my standard talk with a little twist and just ask some questions about what differentiates things like us from viruses and thermostats, and just drill down on the nature of agency and why certain things have the capacity to plan and look into the future. So we're going to start with this question posed by Schrödinger. How can the events in space and time which take place within the spatial boundary of a living organism be accounted for by physics and chemistry? Now, we're not going to answer that question, but what I want to do is just pick out this notion of the spatial boundary and just note, in order to talk about anything, you have to be able to distinguish or individuate that thing from everything else. And I'm going to read that boundary as a Markov blanket. A Markov blanket essentially being a statistical veil or insulation that separates me from the rest of my universe. And I've tried to illustrate that here with this little graph, where we can imagine that these circles correspond to states of some simple universe, and the arrows correspond to the influence of this state on that state. And technically, the Markov blanket comprises the parents, the children, and the parents of the children of the internal states. So this means that there is a subset of all the states of the universe that provides an insulation or separates me, my internal states, from all my external states. Mathematically, what this means is that I only need to know these states, the blanket states, in order to predict the evolution of the dynamics of my own states. The internal states are conditionally independent of the external states if I knew or given the blanket states. And I'm going to make a further move here, and I'll explain why in a second. I'm going to divide the blanket states into active states that influence but are not influenced, into sensory states that influence but are not influenced by internal states, and active states that influence but are not influenced by external states. And that partition allows me to talk about particles, or the states of a particle in terms of their internal states, say my internal states, and my blanket states that comprise my sensory and active states. So why have I chosen that particular partition? Well, if you think about anything in the physical and life sciences, that dependency structure, that sparse coupling, those particular patterns of influences emerge in everything that you can imagine. For example, if we take a brain, we can imagine that the internal brain states are neuronal activities and synaptic connectivities, and they influence our actuators, our muscles, our autonomic nervous systems that cause changes in the external milieu, which could be my body or my extrapersonal space, that then reciprocate and influence my sensory epithelia, my sensory states, that then change my internal states. And in exactly the same way, we can understand the self-organization of a single cell, with intracellular states being internal states that say might influence the actin filaments that support the cell surface, or the sensory states that push into the external milieu that reciprocates by activating cell surface receptors that in turn then couple back to the internal states. So the picture here is a kind of circular causality that you could understand as a generalized action perception cycle. You could also understand this as a way of opening up exchange between the inside and the outside of me, whilst preserving a distinction between my states and everything else, because that exchange is mediated via these blanket states, the sensory and active states. So what I would like you to do now is just forget about the Markov blanket. What we're going to do is do a very brief course in physics, and then put the Markov blanket back and see what special kind of dynamics or mechanics emerges, and how we might understand that in terms of cognitive science and machine learning and intelligent behavior. So if you forgive me, I'm just going to very briefly rehearse some key bits of physics that we're going to need to get at this Bayesian mechanics. And I'm starting off with a notion of the universe that can be described in terms of changes in some abstract states, very high dimensional states, that are controlled by or prescribed by the flow of the states that is state dependent, plus some random fluctuations. So I've drawn this out here in terms of the trajectory of some states, and it could be any states and it could be any time scale. So it could be oscillations in one of my hippocampal neurons, it could be progression through the different phases of the cardiac cycle, it could be me getting up in the morning, having a cup of coffee, doing my emails, it could be over a year, Christmas, Easter, summer holidays. The important thing about this structure is that every time scale and every partition of my state space, I keep coming back to states that I was once in. I keep revisiting characteristic states that characterize the kind of thing that I am, and I won't be found in other states. Technically, this is known as a pullback attractor, a set of characteristic or attracting states. And we can also interpret this graphic in terms of the probability that you will find me in one of my characteristic states if you sample me at any time at random. So we can construe this as a probability density over the kinds of states that I characteristically exist in or encounter. And that's important because if I keep on revisiting the same state, this probability distribution doesn't change. Why is that important? Well, in physics, we know a lot about the way that this probability distribution evolves, the density dynamics. I've written it down here in terms of the Fokker-Planck equation. There are lots of other ways of expressing exactly the same equation, the Schrödinger wave equation, the master equation. The key thing is, if we know that this probability distribution is not changing over a sufficient period of time, the rate of change of the probability distribution itself is zero, which means this thing that is a function of the amplitude of these random fluctuations and the flow, my dynamics, is equal to zero, which means I can write down this very important equation. I've used a Helmholtz decomposition here, which just says my dynamics, the way my states must change, can be expressed in terms of a gradient flow on the log probability of me being in any particular state. It's a little bit more complicated than that. There's a gradient flow dictated by these random fluctuations and a sort of circular flow. Perhaps I can give you an intuition as to what that looks like if you just think about water going down a plug hole. So the gradient flow would be the water going down the plug hole, and this solenoidal conservative flow would be the water circulating around, not changing the level, but moving in circles or in a solenoidal fashion. And the reason for this gradient flow is that in order to stay in the same state, I have to flow up the probability gradient in order to counter the dispersive effect of these random fluctuations. So that's the basic idea. What I want to do now is ask, well, what about that Markov blanket partition that defines something? Exactly the same rule has to apply to both the internal states and the active states. But by construction, neither of these states depend upon the external states. That's how we've defined something, which means that we can now write down the dynamics of internal states as a gradient flow on the log probability of my sensory states. And exactly the same quantity governs the dynamics of my action, my active states. And I'm going to interpret this as a mathematical description of perception and action. And if I do, I can then ask the question, well, what would it look like? Well, it would look as if I'm trying to maximize this quantity here. This is what this gradient operator means. This quantity, the log probability of being in some characteristic states given I am me. So how might one interpret that? Well, we've already got a clear interpretation because those particular states that have a high probability are parts of my characteristic or attracting set. They are the kind of states that it looks as if are attracting me. So they are valuable to me. They characterize me. And therefore, I can read this log probability in terms of reinforcement learning. If I was an engineer, it'd be optimal control theory. If I was an economist, expected utility theory. That's nice because the negative of this same value in information theory is called self-information surprisal, or more simply surprise, which means that at the same time, I can interpret me as perceiving and acting to maximize the probability of occupying valuable states. I'm also, it looks as if I am trying to minimize my surprise or my self-information. And we'll see later that that is exactly what is described by another approach, another sort of theoretical framework to understand behavior in terms of the principles of maximum mutual information, equivalently minimum redundancy, and indeed the free energy principle. The free energy gets into the game because it provides a computable bound or proxy for this surprise, and we'll see the functional form of this free energy at the end of the presentation and unpack it a little bit. In turn, this is nice because the average of surprise or self-information is entropy. So all this is saying is that things that self-organize and have characteristic states are trying to resist a dispersion, a dissipation, and an increase in the entropy of the probability distribution over their states. And of course, that's the holy grail of self-organization, particularly as articulated in synergetics in physics. And of course, if I was a physiologist, it's just a statement of homeostasis, keeping my essential variables within particular ranges, within characteristic values. There's a final interpretation, which I'm going to leverage in the rest of the talk, which is the sort of interpretation that a statistician would bring to the table, namely the probability of some sensory data given not me, but a model of my of the causes of my sensory data. And this will be known as model evidence, also known as marginal likelihood, which means that action and perception can be understood as trying to gather evidence or maximize the evidence for me as a model of my lived world. And this is, of course, leads to the Bayesian brain hypothesis, evidence accumulation, and a particular instance of that predictive coding. So just to illustrate the generality and the simplicity of this kind of self-organization and how we can interpret the ensuing Bayesian brain understanding, or more generally self-evidencing, in the sense that anything that has can be individuated from everything else must look as if it is maximizing the evidence for its implicit model of the world in which it is situated. So what we've done here is just create a little universe, a little primordial soup composed of macromolecules with strong and weak interactions. And because we have written down the equations of motion, we know all those causal influences now, which means that we can go in and ask, is there a little creature living in this soup defined by its Markov blanket? And if there is, can we see any evidence that it's somehow modeling or inferring what's going on outside its surface? And that's relatively easy to show. So what I'm doing is showing exactly the same simulation as previously, but now color coding little molecules in terms of internal states in blue, active states surrounding them in red that support the magenta sensory states that are pushed into the external states in cyan. And what we can see is a little virus-like particle or creature wiggling its tail here, happily occupying its characteristic states at non-equilibrium steady state. So now the question is, can we find any evidence that those internal states are in some sense modeling or inferring or gathering evidence for the external states? And again, it's fairly straightforward to illustrate that kind of self-organization. So what we've done here is pick out a linear mixture of the internal electrochemical states that best predicts motion of the external molecules. So this is a little bit like a synthetic study of visually evoked responses in a brain, for example. And we see a remarkable correspondence between the predicted or the expected from the point of view of the inside of this little particle, the expected motion of the external states and the real motion given by the cyan line, these being the 90% confidence intervals. And furthermore, if I just sort of time lock certain excursions or event-related responses when some of the motion here shows extreme values as little molecules are ejected into space and then come back again, and superpose them, we get a picture of dynamics which is remarkably similar to that which we observe electrophysiologically. This example comes from a monkey study of evoked visual responses as measured electrophysiologically. So this could indeed be read in terms of this self-evidencing or this predictive-like processing or Bayesian mechanics. But there's another slightly simpler way of describing what's going on here, and that's known as generalized synchrony or synchronization of chaos. And I'm sure most of you will know this notion from Christian Huygens, that it is the observation that if you put two or more clocks and suspend them from the same wall or beam, ultimately they will come to swing in synchrony. That is their characteristic, that is state, that is their attracting set of a dynamical sort. And indeed, there's a little drawing from Christian Huygens here, where he's put two clocks suspended from the same beam. And from our point of view, we can treat one of the clocks as the internal states and the other as the external states. And then the beam now constitutes the way in which these two clocks speak to each other, or sparsely coupled to each other, comprising the active and sensory states. And I like this picture because it really foregrounds the symmetry of the argument. So if you subscribe to the view that the internal states are trying to model and gather evidence for the external states, then it also has to be the case that the external states are also modeling you. And there are some interesting interpretations of that in terms of how the environment learns about the kind of phenotypes that it plays host to. But let's summarize now all of this physics. The existence of a particle implies a partition of systemic, namely the states of a system, into internal and blanket states, namely the sensory and active sectors of the blanket, and external states that are hidden behind that blanket from the point of view of any particle or person. And because active states change but are not changed by external states, they reduce the entropy of the blanket states. And this means that action will appear to maintain the structural and functional integrity of the Markov blanket, of the boundary. And you can read this as an elemental kind of self-assembly in computational chemistry, and perhaps in the life sciences, a very simple kind of autopoiesis. And because internal states appear to infer the hidden causes of sensory states by implicitly maximizing or explicitly maximizing Bayesian model evidence or marginal likelihood, they actively influence those causes, and we refer to that as active inference, which is what we'll focus on next through the lens of neurobiology and psychology and sense making more generally. So the story now has I'm going to tell exactly the same story, but now using the language and concepts from the life sciences, and particularly neurobiology and neurophilosophy. This story probably starts with Plato and developed by Kant and Helmholtz and the like, but it's nicely illustrated by this 16th century oil painter famed for painting still lives, that when viewed from a different perspective, give you a very different kind of visual impression. So if previously you saw a bowl of fruit and now you see a face, the point that he's making here is that you made that face. It's something that you brought to the table to understand or make sense of, or to explain this particular pattern of sensory input. Speaking to the fact that the brain, your brain, is literally a fantastic organ. It's a generator of fantasies, hypotheses, explanations, best guesses, constructing the best explanation that explains away those sensory impressions. To my mind, Hermann von Helmholtz is probably articulated this most compellingly and beautifully. For example, objects are always imagined as being present in the field of vision, as would have to be there in order to produce the same impression on the nervous mechanism. And this is clearly very much in the same spirit of 20th century ideas such as perception as a hypothesis testing by Richard Gregory, the notion again that the brain is a statistical organ, a constructive organ, constructing hypotheses, explanations for what's going on, and then testing those hypotheses against the sensory evidence for that. And these ideas have been formalized and used to great effect in computational neuroscience and machine learning specifically by people like Geoffrey Hinton and Peter Dayan, who actually made a Helmholtz machine, and as a metaphor for the Bayesian brain, borrowing from the ideas of Thomas Bayes, and specifically leveraging the work of Richard Feynman on tractable ways of building a Bayesian brain that rest upon this free energy bound that is the free energy, that underwrites the free energy principle. But let's just return to Helmholtz and this notion of impressions on the nervous mechanism, or in this instance, impressions on the sensory sector of my Markov blanket, my sensory epithelia. So if this Bayesian mechanics is right, what it means is it will look as if my internal states, my brain, is trying to make sense of what caused these sensory states, these sensory impressions upon my Markov blanket or my sensory veil, which hides the actual external causes. I will try and infer what caused that. So a natural question is, well, how can we understand the dynamics and mechanics of that kind of perceptual inference? Well, we already know the answer because that comes from the physics. I would just re-express that gradient flow for the internal states here. And I'm going to read the internal states as expectations, best guesses about the external states. And I've replaced that, that value or surprise with its free energy bound here. So we can express the gradient flow of internal states in my neuronal dynamics as a gradient flow on my variational free energy. And I've separated it into the dissipative and conservative parts, the solenoidal and the gradient parts here, and then rearranged this equation in a form that if you were an engineer, you might recognize as a Bayesian filter, and specifically in this instance, a Kalman filter. What does that mean? Well, it means that if I had expectations about the state of the world out there, then I can guess and predict how that world is going to change because I know about its dynamics. And then what I can do is I can update that prediction on the basis of a prediction error that just is the free energy gradient. So what's a prediction error? Well, imagine I had this sensory impression here, and I had some expectation encoded in my neuronal activity that it was caused by a howling dog. And if I had a generative model, denoted by G here, that could generate the predictions of what I would see or sense if I had this belief or expectation, then I could compare my predictions with what I'm actually sensing to produce a prediction error. So this free energy gradient or prediction error is just the difference between what I'm actually sensing and what I would have predicted myself to sense if I had this kind of expectation. And all this equation is saying is that this prediction error is then used to drive the internal states until this prediction error is minimized, or I have destroyed the free energy gradients by finding the minimum of this surprise or negative value. Now notice that what this equation means, and we know that it has to mean this because we know the internal states can never actually see the external states. It just means that I will try to minimize my prediction error. I will never actually know what caused my sensations, and indeed in this particular example, the sensations were caused by a cat and not a dog. However, that provides a really simple and nice account of action and perception in which we can forget about all the physics and just focus on the notion of prediction error. And that tells you immediately that there are two fundamental ways in which we can minimize prediction error. We can either change our mind, literally by changing our brain states, to make the predictions more like the sensations, and we can construe that in terms of perceptual inference, changing the predictions so that they explain the sensory input, or we can act to change the sensations to make them more like the predictions. So this renders action as in the service of minimizing the same prediction error as perception, and also as fulfilling predictions. So changing sensations to make them more like the predictions to minimize the prediction error. And I've shown that, I just try to illustrate that basic notion, slightly nuanced and extended in terms of hierarchical generative models in the visual system. The reason I've done this is just to introduce the notion of predictive coding, and the key aspect that active inference brings to the table, which is the action. How does action get into the game when we're talking about predictive coding in this sort of more in this predictive coding reading of these gradient dynamics? So what we have here is a sketch of the brain, say, for example, starting with visual retinal input coming into the lateral geniculate body, that input being in receipt of top-down predictions that can be used to compare with the actual sensory input to form a prediction error, and then that prediction error is used to drive the expectations of neural activity, trying to explain away that prediction error as described by these gradient flows here. However, this expectation is itself in hierarchical or deep generative models in receipt of predictions, and we have now second order prediction errors that in turn will be used to drive the higher order expectations, and so on to any desired hierarchical level. What I want to do now, though, is just note that there is another kind of input whose prediction errors can be minimized in a very different kind of way. Let's imagine we had some proprioceptive input from our oculomotor system. It comes into the pontine nuclei. It is in receipt of, or it can be predicted, say, from polysynaptically from the frontal eye fields. And we could use this prediction error to revise our expectations or our beliefs in the spirit of Bayesian belief updating about the state of our oculomotor plant, namely where we are looking. However, there's a much simpler way of minimizing this prediction error, and that's to use it and couple it back to the outside world and use it to derive changes in the outside world, namely my muscles, until my muscles supply exactly the signals that I predicted. And this provides a very different view of these descending predictions. They now assume the role of specifying set points for classical reflexes. And this, on many readings, is exactly how we actually work and how many robots actually work, that we actually specify what we'd like to feel, and then we let our periphery, our reflexes, both autonomic and motoric, fulfill those predictions, finding those equilibrium or set points. So basically, predictive coding with reflexes is what falls out of this particular application of the free energy principle to these kinds of generative models. So let me close with a couple of examples of this, and then, as I promised, the final twist. So what we've been talking about thus far is a picture of sort of belief updating in the brain that can be described in terms of free energy minimization at two levels, in terms of perception and action, namely perceptual inference and action selection, where we have the external states generating sensory information that comes in and is used as an argument for this computable bound on negative value or surprise, used to optimize some beliefs about the external states, the expectations that we're talking about in the previous example. And then those beliefs about the state of affairs in the outside world are then used to generate a prediction about how I am going to move. And then those predictions specify action via the gradient flow on active states in terms of prediction errors, but just prediction errors about the proprioception, about the state of the motor plant. We can illustrate this kind of phenomena by creating little agents and then specifying a generative model that in turn specifies the free energy, and then we can just simply integrate those equations, those neural dynamics, using that predictive coding or Kalman filter, or more generally this gradient flow on the ensuing free energy, and we can reproduce quite sort of biomimetic like behavior. This is one example. It's an example I like because it sort of highlights the fact that you can often author your own sensorium. You can actually create changes in the environment that generate the kind of autonomous dynamics and activity that you think you are going to prosecute. But in fact, the world is actually changing on the basis of your predictions as opposed to you predicting the world. So let me just unpack that in terms of this particular simulation. What we've done here is write a generative model down that has autonomy. It has dynamics in the form of a central pattern generator, mathematically a heteroclinic cycle that just describes dynamics where some abstract attractor state circulates around some unstable fixed points. And the key thing here, what we've done is equip this agent with a generative model such that these abstract movements or points in this abstract state space map to points in extrapersonal space. And furthermore, this agent thinks that there is a spring between this invisible point and the tip of her finger. So she expects to both see and feel her finger being pulled around in some systematic way. And we can use this to simulate not unrealistic handwriting movements, for example. So here, because she expects to feel her finger moving, then reflexes will fulfill those predictions and her finger will move, at the same time providing the visual input that was predicted by what we can read in terms of the corollary discharge. And then if we go and look at the dynamics, they bear a remarkable similarity to the kind of dynamics that people study in electrophysiology. So there's one particular example here where we're focusing on the activity of this unit, and every time it surpasses half its maximum activity, we just plot a dot as a function of where the finger is. And what this shows is it shows a receptive field, a functionally selective response, very much like a place cell would. And furthermore, it shows a directional selectivity. It prefers the downstroke of the J as opposed to the upstroke. And the further nice thing about this kind of simulation is that now I can remove the proprioceptive input and simulate what it would be like if this agent saw the same thing but could not feel her arm moving or her finger moving. In other words, what it would be like if she saw somebody else doing the same actions. And she can predict this and explain this perfectly well because she's got the right kind of generative model in order to predict the visual input. And if we replay exactly the same visual input, we activate effectively exactly the same representations here. It takes a little bit longer to recognize what's going on, but once it has been recognized, the trajectory of the inferential dynamics, those gradient flows, reproduce the same selective responses in particular synthetic neuronal populations of the kind you'd expect to see in the mirror neuron system. So all of that depends again on this sparse coupling that individuates me from the rest of the world. What I want to do in closing is make one small move, which has an enormous implication for the kind of self-evidencing that we've been talking about, and hopefully provide a distinction between that kind of reflexive behavior that we just described, which is quite expressive and can accommodate lots of biotic kind of action, but it doesn't really account for the way in which we make sense of our world and specifically the consequences of our actions when we start to think and plan and make choices on the basis of what would happen if I did that. So where does that kind of sentient behavior come from in this framework? Well, it's very simple. Imagine that I'm very big, and my internal states are hierarchically composed in such a way that I no longer have direct access to my actuators, my autonomic reflexes, or my actual movements in the world. So I'm just going to remove this arrow here. And that has quite a profound consequence. What it means is I now am in the position of having to treat my own action as a vicarious cause of my sensory states of my Markov blanket. In other words, now action becomes a random variable that I have to infer. And what this leads to effectively is planning as inference. So I've tried to cartoon that here in terms of what it would look like from when interpreting self-organization through this lens of self-evidencing on Bayesian mechanics. If I removed that particular connection here, and we move from an understanding of or interpretation of neural dynamics in terms of some organism or creature or particle having beliefs about the external causes of its sensations, to this more elaborate structure where now we include action in the belief structure. So now we have beliefs over both external states and my own action. And what does that mean? What kind of actions then would I believe I should be pursuing, and in so doing actually enact those beliefs? Because if you remember, action itself is just trying to fulfill predictions, self-fulfilling prophecies. What happens is that we now equip our computational anatomy with effectively planning as inference, basically evaluating the probability of various trajectories into the future based upon the notion that the consequences of my action will minimize the free energy I expect in the future. So what's the functional form of this expected free energy? And this is the naughty slide with lots of equations on, but I can't resist showing it. I'll take you through it briefly, give you one more example, and then finish. So what I've done here is written the free energy that underwrites perception. And I've written it in two ways that different people or different communities would recognize. If you were a statistician, you would recognize this as a mixture of accuracy and complexity, the log probability of some sensory data given the explanatory variables or the hidden states or the external states. And I'm trying to basically adjust my beliefs or state estimation in order to provide an accurate account of those sensory data. But crucially, under complexity constraints, I'm going to minimize the degree of belief updating, trying to keep my posterior beliefs as close as possible to my prior beliefs. And that's known as complexity in statistics. Just by swapping around a couple of these terms, I've expressed it as somebody in machine learning would normally express this in terms of an evidence bound. Why? Well, because this quantity here is just the log evidence, the log of the model evidence, and the other term is a divergence that can be never less than zero. Therefore, this quantity, this variation free energy, provides a bound on the log evidence. And the reason I've written it out like that is that now when we consider the consequences of moving, bearing in mind that those consequences are now random variables because they have yet to be realized, I now have to take an expectation over those sensory consequences, and then these quantities here become expected complexity and expected accuracy and expected divergence and expected log evidence. And what we see is that we can interpret this in terms of risk and ambiguity, or a mixture of intrinsic and extrinsic value. So let me explain what these things are. You will probably recognize most of these things, but I think this is a very compelling deconstruction of the imperatives for action and action selection. So I'm going to ignore the extrinsic value at the moment. Everything, I don't mind what happens to me, and I'm left with this. What is this? It's just the information gain or the resolution of uncertainty that I would have if I took an action and got some sensations. So technically it's a KL divergence, or the difference between beliefs about external states given the sensory information ensuing from a particular action relative to those beliefs before seeing that particular sensory outcome. And this is known as Bayesian surprise in the visual search literature. More generally, it's just the mutual information between causes and consequences, external and sensory states. Let me now take a certain kind of uncertainty off the table and remove the ambiguity. I can see everything, so the sensory states become the external states and vice versa, and I'm left with this. And this is called risk. It's just a KL divergence between what I expect to see if I do this relative to what a priori I prefer to see, the states that characterize me, my valuable states. So this in engineering is known as KL control, or in economics, risk sensitive control. And finally, if I remove the last kind of uncertainty, there's no more epistemic uncertainty, there's no more epistemic affordance, there's no more exploratory drive, because I know everything that I can know about this particular environment. Now I'm just left with this, which we know is the expected value or the expected utility in an economic sense. So in brief, we've got from a sort of very general formulation that emphasizes the epistemic aspects of Bayes optimal behavior through to the much more pragmatic, extrinsically driven aspects, which are much more consistent with reinforcement learning and Bayesian decision theory. So I'll close with an example of that, focusing on this epistemic affordance, which can be read as salience, and illustrating this in terms of gathering information in a smart way that maximizes the expected information gain or minimizes the uncertainty about what could have caused my sensory impressions under the constraint that I can only sample a small part of the visual field at any one time. And if I move this sampling circle here around and score the information gain or the resolution of uncertainty, I produce a salience map, which is apt for describing human behavior, and I can simulate that. This is a very simple illustration where this agent had a very simple universe. It could see an upright face, a sideways face, or an inverted face, but could only sample little portions of the visual field at any one time. So it has to decide very carefully where to look next, and clearly that is exactly prescribed by the salience or the expected free energy. And here are the sort of salience maps that evolve over time as my beliefs change, or this agent's beliefs change, and the kind of uncertainty to be resolved itself changes. Here are the sensory samples and the resolution of uncertainty as this agent correctly infers that it is looking at an upright face. So that's it. That's the final example, which emphasizes this planning as inference that underwrites our active engagement with the sensorium. It can be much more succinctly summarized by Helmholtz. Indeed, he has done so here. Each movement we make by which we alter the appearance of objects should be thought of as an experiment designed to test whether we have understood correctly the invariant relations of the phenomena before us, that is, their existence in definite spatial relations. And with that, it only remains for me to thank those people whose ideas I've been talking about. And of course, thank you for your attention. Thank you very much indeed.
Thank you very, very much. Dr. Gouveia, would you like to lead the discussion?
Yeah, so sorry about the beginning, but you did a great job. Hi, Karl, again, for the fifth or sixth time. Hope you're well. So let me start by saying that every time I hear a talk from you, I feel I'm getting like a second PhD in mathematics, physics, and neuroscience, all in the same place. So yeah, so my brain is a bit tired, but I have just one question, because I think we have really interesting questions from the audience. So I have two questions. I will make first one. Do you really think that the free energy principle is a truly unifying principle in neuroscience? And that is my first question. And the second question is just, there is a big controversy right now about the information integrated theory that was labeled as untestable and pseudoscientific. So do you recognize those labels in this theory? And do you think the same could be said about your approach to the brain and the mind? So those will be my two questions.
Right. We have to answer those in the remaining 10 minutes. Sorry, they're very challenging. And thank you for those kind comments. So yes, I do think that the free energy principle is a unifying theory, simply because it inherits from well, first of all, simply because it inherits from straightforward physics, and it has exactly the same foundations as quantum mechanics and statistical mechanics and classical mechanics. And the Bayesian mechanics is just another flavor of exactly that kind of physics that is specialized when you have a Markov blanket. So it's just a physics of things. In that sense, I think it is unifying, and it's furthermore unifying in the sense that, you know, things that emerge under this framework, everybody recognizes, from sort of reinforcement learning right down to, you know, self-evidencing in the spirit of Jacob Haig. In terms of the more vexed issues about pseudoscience and IIT, in brief, I do not think it is appropriate to call IIT pseudoscience. I think that was something that will probably be removed following the Twitter storm from the peer-reviewed literature, at least, and possibly the open letters. What's the relationship between IIT and the free energy principle? I think that's a slightly more, again, vexed question. The free energy principle is not a theory of consciousness. It's a theory of very basic sentient behavior and self-organization. But you'd have to do a lot of work to say what kinds of things could be conscious and have qualitative experiences, and furthermore, a lot more work to define the kinds of generative models that would support certainly things like minimal selfhood and indeed self-awareness. So the free energy principle doesn't do that. You can apply the free energy principle to certain generative models and start to ask, you know, what kinds of systems would you need? And the answer you come up with is actually quite close to IIT in one respect, although there's a lot missing from IIT from my perspective. But the point I'm making, IIT is meant to be a theory of consciousness, so it's got its own rules to play by. Having said that, many of the sort of more basic formal consequences of the axioms of IIT do emerge for free under the free energy principle. So I actually see a lot of consilience between the conclusions of IIT and the kinds of certainly, you know, in terms of the information theoretic reading of the free energy principle, there's lots of similarity. But you know, that's one, you know, I repeat, there are things in IIT, there are things in the free energy principle that are not in IIT, and IIT comes from a different stable. It's an axiomatic theory. It's not a first principles theory.
Right. Perfect. So we have two questions from the audience. So the first question, I will make it very briefly. So it's about the relationship between your work and neuropsychoanalysis. So do you think your work can give a new flavor to psychoanalysis and achieve what Freud meant by scientific psychology?
Yes. Yeah, I think. Yes, I think that's a great question. Yes, I think you can. But more importantly, scholars in neuropsychoanalysis think you can. So people like Mark Soames and his colleagues have, I think, put an enormous amount of work and thought into exactly a revisiting of Freudian formulations in the 21st century using the lens of the free energy, or applying the free energy principle, and I think in a very compelling way. Just, you know, one reason you might think that would work is that when Freud was trying to formulate his notions, he would have been acutely aware of the work of Helmholtz, and Helmholtz himself was himself trying to find a generic expression for a neural energy that explained the kind of behaviors and sense making that we're talking about, above and beyond his thermodynamic Helmholtz free energy. So he was on a mission to, I think both of them were on a mission to try and find some kind of free energy, but both of them predated Feynman, and it was Feynman who actually formalized and naturalized this particular application of free energy and understanding it in terms of rendering an impossible inference problem, a marginalization problem, into a tractable optimization problem. So you will see in the writings of Freud, it's all, you know, it's all about optimization forces and repressions and the like, which inherits, I think, directly from the mathematical structure of the free energy. I should also note that, you know, had Freud and Helmholtz been able to talk to somebody like E.T. James, you know, 50, 60 years later, they may also have been able to naturalize their definitions of their free energies or the neuronal energies anyway, in a way which would look, I think, formally identical to the way that we do it now. And indeed, you can read the free energy principle as just a different kind of or interpretation of James's maximum entropy principle. It's slightly different because it brings to the table the Markov blanket, but otherwise there's a common story, I think, over the century that could, certainly includes Freud. Yeah.
Okay. So I will make one more question from the audience. So I'm not sure how to pronounce the name, but it's Catalina Balam, and she asked, are there potential applications of these principles in the development of advanced assistive technologies for individuals with disabilities, particularly in terms of enhancing their ability to interact with the world? Thank you.
Right. Yeah, again, it's an excellent question. Yeah, in principle, to understand how you couple to the world in a formal way certainly gives you certain perspectives on, say, sensory substitution, and certainly gives you certain constraints on restoring lost motor function and the like. And in principle, you certainly can apply the free energy principle. I should say that in some way it probably already has been applied. I repeat, the free energy principle is not some new idea that replaces all existing idea. It's unifying in the sense that it just naturalizes existing ideas within a sort of a formal framework. But one particularly interesting application, at least conceptually, of this, say, to neuro rehabilitation, is the notion that the brain is built to destroy free energy gradients or minimize prediction errors or learn from prediction errors. So prediction errors are the source of learning. So if you want to, in a neuro rehabilitation context, optimize learning, what you would want to do is to present them with the right kind of prediction errors. So contrary to commonsensical or intuitive practice, you wouldn't get them to rehearse a lost function. You'd actually make it very difficult for them and provide lots of prediction errors in terms of, so that they could use those prediction errors to actually learn most efficiently. So that's one very small, very colloquial example of how you might apply the insights of a generic sort from this view of active engagement and active sensing in a therapeutic context. I could wax lyrical about applications in psychiatry, where you get where you leverage the notion of the brain as an inference machine to understand psychopathology in terms of false inference and what the lost mechanisms are there. But we don't have time to go there, but just to celebrate the cleverness of that question.
Perfect. So I think we have to go. Thank you for having me again. And I will now give the word to Christina.
Yes, thank you. Thank you very much again. Thank you, Professor Friston. It's been truly an honor to have you here, and we are very grateful that you could join us today. And thank you, Dr. Gouveia, for leading the discussion.